this page here. This has a little bit of everything in it, okay? There's a couple of things on here that we haven't used before, so I wanted to kind of point out a couple of things here and talk about some of these. So we're just going to kind of do these together and talk about some of the different statements that might be used. Now, there is a bank at the bottom. Some of those things that we've talked about, some of them we really haven't. So some of these are going to be a little bit new for statements that we're going to use. And so we're not necessarily doing a proof here. We're just providing a reason or a statement or a postulate as to why we are saying what we're saying. Okay, so if I don't have a symbol above PQ, what's that saying? That what?
Points.
Okay, P all by itself is a point, but what about PQ with no symbol above it?
It's a line, not a segment.
So a segment will have, a line would have a line with arrows on it. If no symbol above it means it's a measure, it's distance, okay? So here we're talking about the length of PQ. So we're saying here, if the length of PQ equals the length of PQ, then PQ is congruent to PQ, okay? This is what we call the definition of congruence, okay? If two things have the same length, then they are congruent, okay? And that's down there in your definitions in the bottom in the bank. That's how it's used. If two things have the same length, then they are congruent. Okay, number two. If K is between J and L. Sometimes I think drawing out a picture might be helpful. Here's J, here's L, here's K. And what they're saying is JK plus KL equals JL. What are we using here? What are we doing?
Adding segments.
Adding segments, okay? So look at the bottom. What would we use here? We used this one yesterday. Segment addition postulate, good. Because we're adding segments. So just ask yourself, what's happening? Here we're adding segments, so we call this the segment addition postulate. One of our proofs yesterday, and we did the segment addition postulate in our notes yesterday, and then I think it was like very first example, the very first homework problem you had, it was an angle, and I still had people writing the segment addition postulate, but we weren't adding segments, we were adding angles. So there's also an angle addition postulate. I don't think it's on this page, so we didn't include it in the property bank, but angle addition postulate is another one. Two small angles add up to equal the big angle. Okay, EF is congruent to EF. What do I know about, or what do I notice about both sides? They're exactly the same. And if two things are exactly the same, what do we say? Reflexive, okay? And I'm going to call this one the reflexive property of congruency, because it has a congruent symbol between it. If it had an equal sign between it, it would be equality. And that's why you see properties of equality on the left and properties of congruence on the right. There is, if you notice, reflexive, symmetric, and transitive are in both lists. So we got to identify which one.
Will we lose points on the test for not specifying equality or congruence?
Maybe so, yeah, because there are two different ones, yes. But you can just put the symbol, you don't have to write out congruence or equality. Okay, if RS is equal to TU, and RS plus XY equals TU plus XY, what's happening here? Okay, notice what's going on here. Okay, RS equals TU is given to us at the beginning. What did they do to both RS and TU? They added XY, right? So we're adding the same thing to both sides. Whatever I add to one side, I have to add to the other. So what do we call that? So symmetric property just means we're going to flip-flop sides. It would just be addition, because we're just adding XY to both sides. So the addition, property of equality. Okay, we started with RS equals TU. We added XY to both sides. Whatever I do to one side, I have to do to the other. Okay, number 5, AB equals DE, DE equals AB. All I did was take the two statements and flip them over. Symmetric. Yep, when two things are flipped over, it would be symmetric. And this is the one that has two of them. So this is the symmetric property, and between the statements is an equal sign. So it'd be the symmetric property of equality. Okay, number 6. If y is the midpoint of xz, then xy equals yz. How do we know that x, y, and zy are congruent? Definition of midpoint, good. It might be just as easy, it might be just use what's told to us in the statement, right? We know it's the midpoint, and then you just think about what does it mean to be the midpoint. Midpoint means it's right in the middle of the two endpoints of that segment. Okay, FG is congruent to HI, HI is congruent to JK. So notice here that we have two statements that are a little bit different, but do they have something in common? Yeah, what do these two statements have in common? HI. So if they both are congruent to HI, then what can we say about FG and JK? They're congruent. What are we using here? Transitive. We're taking two statements, combining them together to make a third. And what symbol are we using on all three statements? Congruence. So this is the transitive property of congruence. Okay, this one's kind of tricky. And the reason I'm showing you this, because I think this is what's going to make more sense to you, rather than looking at it as a big old statement. Okay, here's what we're starting with. Okay? Here's what we're ending with. This is the then statement. It's our conditional that we talked about at the beginning of chapter 2, right? If this, then this. What disappeared? Here's what we had. Here's what we have now. The CD's gone, right? What did they do to get rid of the CD? They subtracted it, right? So they're just subtracting CD away from both sides. So this would be the subtraction property of equality. Okay. Number 9, if PQ plus RS equals TV and RS equals WX, then PQ plus WX equals TV. What did they do here? They substituted it in, right? They're saying RS and WX are the same thing. So they took WX and put it in where RS was. So they took something and replaced it with something that it was equal to. Be careful with abbreviating. I'm okay with abbreviations, but since you have subtraction and since you have substitution, you don't just want to say SUB, because then are you talking about substitution or are you talking about subtraction? Okay? So those are the two you got to be really careful of abbreviating. Okay, number 10. If LP equals PN, and LP and N are all on the same line or segment, collinear, then P is the midpoint of LN. If they're congruent, then what's that tell me about P? P is the midpoint, right? So what do you think we're using here? Not quite transitive. Yeah, definition of midpoint. That's just defining what midpoint is. We know it's the midpoint, so we know that those are congruent. If we know they're congruent, then we know it's the midpoint, okay? It's one of those biconditionals where it could go either way. I could tell you they're congruent, so I know P must be the midpoint. If I tell you P is the midpoint, then I know they must be congruent. It could go either direction. That's what we talked about with biconditionals early on in the chapter. And I bring that up because that's where all of this is being used, right? You might say, well, why did we talk about conditionals, versus biconditionals, all that stuff early on in the chapter? Because look how all of these statements are written. If this, then this. If this, then this. These are all conditional statements, right? And so when we did it early on in the chapter, they weren't necessarily always geometry, but now we're getting into the geometry use of these conditional statements. If UV is congruent to UV, then UV is equal to UV. We had one very similar to this. Definition of congruence, just like number one. They just stated it in a different order, but it's still the definition of congruence. Okay. Take a look at this statement here, and then take a look at this statement here. Okay? The one thing that we notice is that we are subtracting DE from CE. And then over here, notice what happens. My DE is gone. Why do you think that DE is gone? What are they doing? Subtracting. Yeah, exactly. They're subtracting DE from both sides. So that's the subtraction property of equality. Okay? And I truly do feel like it helps to cover up. Look at the beginning statement, where they started. What did we do to get here, right? If this, then this. How are we going to get from here to here? That's the goal when we do these. All right. Let's look at the proof packet. We're going to do one together from this proof packet. Okay, this is the one we're going to do together. I'm going to go ahead and make a two-column proof because it says to complete a two-column proof for the following given statement. Okay, step one. First step's the easy step. Okay, and let's just take what they tell me and use that to make a statement. What does it mean to be a straight angle? 180 degrees. So I'm going to write a second statement, and I'm going to say angle AOC is equal to 180. And we know that because we know what a straight angle is. We've defined it. Whenever I see straight angle, I know it's always 180. Okay? So that's just simply the definition of a straight angle. Okay. And we saw this next step, we saw this yesterday on one of our proofs that you had to do on your homework. This angle plus this angle equals the big angle, okay? That's going to be my next step. Angle AOM plus angle COM equals angle AOC. What are we doing here? What's my reasoning for that? Like, look back at number 1 on your 2-5 practice from yesterday. We're doing the same thing there. Hannah? Angle addition postulate. We're simply adding 2 angles together to get the big angle, right? And that was the one I was telling you guys about, that a lot of people were putting segment addition postulate, but we weren't adding segments, we're adding angles. So it's the angle addition postulate. What we're adding tells us the name. Okay, once I have this statement written out, do I know what AOM really is? Look at the picture. Do I know what's the expression for AOM? 2x plus 30, right? It's labeled right here. Do I know what COM is? X, right? Do I know what AOC is? It's not labeled on the picture, but guess what? Step 2, we know it, right? So do I know all 3 of those? What they are equivalent to? So AOM is 2x plus 30. COM is x equals 180. And all we did there was substitute the values in for the angles. We know what they're equivalent to, so we're substituting it in for what they're equivalent to. Hey, and I truly feel like once we're to this point, it took a little bit of work to get here, right? But once we're to an equation, do you guys all feel confident that you can solve an equation out? Yeah. Okay, and so this is kind of the hard part of the new part that we haven't really done before, but once we're here, we should be good to go, right? So our goal is to get to the point where we have an equation set up, because what we're doing here, look at the proof statement. We're trying to solve what is x equals 50. We're trying to prove that x equals 50, okay? So what would be my next step if I'm going to solve this equation out? Combine like terms, good. Okay, and this is kind of a long one, I know, so I'm going to probably be running out of room here. 3x plus 30 equals 180, and that is combine like terms. Okay, number 6, what are we going to do? Subtract 30, okay? So we're just going to write 3x equals 150. Because we did the subtraction property. And then finally, we're going to divide by 3. The good news is we did all that work and we got to the point where x equals 50. So those two should match up. Now we know that we're done. And there we did the division property of equality. Okay, it's probably the longest proof that we've done. 7 steps, but I don't think there's really any way that we could shorten it down. If we could shorten it down, I would have shortened it down. But each step is important to getting to where we ended up at. To theorems and postulates that we're going to talk about today. And these are some things that I would say they're kind of straightforward, but we need a theorem to kind of state it so that we have a reason why that we can prove whatever it is that we're trying to prove, okay? And so a lot of these things are things that we've talked about as we've gone throughout the first couple of chapters, but we're now going to kind of tie them together into some postulates and theorems, okay? So first one, right angle congruence theorem. Whenever I hear or say the word right angle, what's that mean? 90 degrees, every time, right? If I said acute angle, I don't know what the measure is because I just know that it's a small angle, right? But if I say right angle, I know without a doubt it's 90 degrees. And so if it's a right angle, that means any other right angle that would be a right angle would be congruent with it. All right angles are 90 degrees, so all right angles are congruent. That's what we call the right angle congruence theorem. And like I said, pretty straightforward, right? Because we know it's 90 degrees, they have to be congruent. Okay, if we break this one down, congruent supplements theorem. Okay, the congruent supplements theorem, what does the word supplement tell us when we see that? What are we thinking? 180, right? We've talked about that for a little bit now. Supplement means 180. If angle 1 and angle 2 are supplementary, and angle 2 and angle 3 are supplementary, then angle 1 is congruent to angle 3. So here's how this works. If I said 30 plus 150 equals 180. If this is angle 1 and this is angle 2. And then I said 150 plus 30 equals 180. So this would be angle 2, this would be angle 3. Well, what's happening here is I'm using angle 2 twice. And because angle 2 is the same, that means angle 1 and angle 3 have to be the same as well. Okay? Because what they have to do is they have to add up to be 180. So basically, if you have two angles that are supplementary with the same angle, then those two angles must be congruent. And then the next one is doing the same thing, except instead of doing it with 180, complementary means what, Adrian?
Yeah, I'm gonna pay attention.
Okay. Durston, what do you think? It's Adrian's fault, right? Adrian's talking to you.
No, it's my fault.
What does it mean to be complementary? 90, right? It's got to be 90, right? So I have two angles that add up to be 90. So if I had like a 40 and a 50 degree angle that were congruent, or complementary, sorry, then if I did 50 and 40, then because they're both complementary with the same angle, then those two must be congruent. The two 40 degree angles would have to be congruent. So I'm not necessarily going to write out that one, but it's very, very similar to supplementary. The only difference between those two theorems is supplementary is 180, complement is 90. Okay, linear pair. If two angles make a linear pair, what does it mean to be a linear pair? Linear is a line, okay? Pair means two. So two angles that make a line. So how many degrees would that be? 180, okay? So therefore, if two angles form a line or a linear pair, then they must be supplementary, which is also 180, right? Supplementary means 180. So big key here is to know our vocab. Know what it means to be supplementary. Know what it means to be complementary. If we know those things, then we're going to be in good shape. Okay, we have talked about this a lot, and I told you that these are going to be angles that we're going to see a lot throughout the year. If two lines intersect one another, then the two angles across from one another are vertical. And not only are they vertical angles, but they are also congruent. Those two angles will both be 50 every time, okay? We call those two angles vertical angles, and we know from now on, anytime we see vertical angles, they will always be congruent, okay? The two angles across here would also be congruent as well, okay? So these two are the same, these two would be the same as well, whatever that measurement would be. So I'm going to mark these as being congruent as well. So whenever two lines intersect, we have two pairs of vertical angles. And those two pairs are both congruent. Okay, I'm not going to do the proof at the bottom of this page for right now, okay? I'm going to move on to the next page. All right angles are congruent. So that was the right angle congruence theorem. We're going to do some problems with vertical angles here. Okay, and really with vertical angles, it's pretty straightforward, okay? Especially for this very first example. Angles 1, 2, 3, and 4 2 and 4 are vertical angles, 1 and 3 are vertical angles, okay? And they tell us that angle 1 is 125. So I'm going to go ahead and label that. What other angle would be 125? Angle 3, right? Like I said, it's pretty straightforward. The two angles that are directly across from one another, where the two lines meet, are always congruent. Every time. Okay? The other two, angle 2 is congruent to angle 4. We know those two are vertical as well. We know those two are also congruent based on what we just talked about. Can I find the measure of 2 and 4? Yeah, because what do 1 and 2 form? Supplementary. They're a linear pair, right? These two together make a line, so they are 180. So I can take 180 minus 125. So angle 2 and angle 4 both equal 55 degrees. Okay, pretty straightforward. If I know one, I should be able to find the other three. Hey, in this picture down here, these two angles are directly across from each other. So these two are vertical, right? If they're vertical, what are they also? Congruent. They're equal. Yeah. So 3x plus 1 equals 148. And what this one's asking us to do is it's asking us to find the value of x. So once we have the equation set up, now we just got to solve, right? So now it's just getting x by itself. So we're going to subtract 1 and divide by 3. X equals 49. Okay. One thing I will point out is make sure you understand the difference between finding an angle. Like up here, it asked us to find angles 2 and 4. Down here, do I need to put a degree symbol on 49? No, because x is a variable. X is just a value for x, right? So 49 is the value of x. It's not an angle measure, okay? So we don't have to put a degree symbol on it. But if I'm finding an angle, I should put a degree symbol on it to show that it's an angle measure. All right, last one on this page. We are finding A and B, okay? And the first thing that we know is that these two angles all are vertical, okay? There really no information has to be given for us here, okay? Because we have two lines that are crossing, immediately I know these two are congruent, I know these two are congruent, okay? I don't have to really have any information provided like we do in some cases. So here I'm going to do 7a plus 33 equals 10a minus 12. And we're going to solve for a. Okay, I'm going to combine two steps into one here. I'm going to subtract 7a from both sides. And at the same time, since I'm moving a to the right, I'm going to move my numbers to the left. So I have 45 equals 3a. So a would be 15. Okay, basically the same thing for B. B would be these two angles here. So I'm going to go 6b minus 42 equals 3b. What would I do here first? What would be my first step? Yeah. And the reason I ask that is because it's probably not what we would choose to do, because when I subtract 6b from both sides, what happens? It becomes negative, okay? And I know sometimes we like to avoid negatives, and there's nothing wrong with that, but in this case, because negative 42 is over here all by itself, then that's probably why we would choose to do that. We could flip-flop them, right? We could add 42 and subtract 3b, and that would be okay too. So there's a couple different ways that we could approach this, but it's okay if we have negatives. It's not that big a deal, because now if I want to get b by itself, I'm going to divide by negative 3, and I get 14 equals b. Okay, so that's just solving some problems out with vertical angles, finding missing values, finding missing angles, that kind of thing. Okay. On the next page, what we're going to do is we're going to use some of those theorems that we just talked about to write a proof. Okay, so we've got this picture, and we're trying to prove angle 1 is congruent to angle 4. Okay, angle 1 and angle 4 are congruent. Oh, sorry. We're trying to prove angle 2 is congruent to angle 3. Angle 1 and angle 4 are given. That's my fault. Whenever it says is given, that's our first statement. Okay, given statement, first statement should always be the easy one. Okay, based on what we know about this picture, what would be true about angles 1 and 2? They're congruent. Okay, what would be true about angles 3 and 4? They're congruent, because what kind of angles are they? Vertical. Okay, and here's what I'm going to show you guys is I could do this in 2 separate steps if I want to. Angle 1 is congruent to angle 2, but I'm going to write this in just one step because they're both using the same reasoning. Okay, if I use the same reasoning, I don't necessarily have to write it out as 2 separate steps. It's not wrong to write it out as 2 separate steps, but we can combine this into one. Okay, and our reasoning here, we're just going to try to keep it as simple as possible. All vertical angles are congruent. If I have vertical angles, they are congruent. And we know that those are vertical. Okay, so now what we need to do is we need to prove that angle 2 is congruent to angle 3. Okay, somehow. Any ideas? Okay, let's cover this up. Look at these 2 statements here. What do those 2 statements have in common? What's angle 4 congruent to? 1. What's angle 2 congruent to? 1. So if angle 4 and angle 2 are both congruent to angle 1, then what do I know about 2 and 4? They're congruent to each other, right? So what I'm going to say here is angle 2 is congruent to angle 4. Any idea on what that property is or what we're doing there? Why? What's my reason? Anybody remember what that is? When I take 2 statements, combine them together to make a third? Transitive, yeah. It's a transitive property. And because we're doing congruency here, we're going to say the transitive property of congruency. A couple days ago, we talked about the reflexive, the symmetric, and the transitive property of congruency. We could do equality, but because all of our statements here are congruency, we're going to use congruency here. Okay, are we done? Have we proven what we need to prove? No. Our goal is to prove 2 and 3 are congruent. So now look at these 2 statements. What's 3 congruent to? 4. What's 2 congruent to? 4. Since they're both congruent to 4, then what can we say? 2 is congruent to 3. Okay? And that's where we wanted to end up at. So we're going to say angle 2 is congruent to angle 3. Hey, what do you think our justification is going to be? What's our reason? Transitive again, right? We don't want to overthink it. We could use, now this one we do have to separate the two steps because I had to do step 3 before I could get to step 4. I had to prove this first before I could get to here. So this one we did have to separate it out a little bit. And that's our proof. We know that we're done when it says to prove this, and that's our statement. Okay, that's how we know we're finished. Okay, questions on that one? A little bit different proof, okay? We're just trying to show you some different variations of some proofs here. Okay, let's look at this one here. Bunch of given statements here. A, B. What does the upside down T mean? Not quite. Perpendicular, yep. AB is perpendicular to BC. DC is perpendicular to BC. Okay, that is my given statements. So what does that tell me about angle B and angle C? If two lines are perpendicular, what do we know about them? What are they doing? Okay, they're intersecting and they're right angles. Okay, and so immediately I can conclude that angle B equals 90 degrees. Angle C equals 90 degrees. I don't really need 3 letters here because that's the only angle at B and C, so I can just call it angle B and angle C. What's my reasoning for saying that? Why can I say that those are 90 degrees? How do I know that? It is the right angle symbol, but what if that right angle symbol wasn't there? I'm with you. It's already there, so that's kind of how we know that. But let's say that that wasn't there to begin with. Hannah?
Because they're perpendicular.
Okay, and so you're right there. Okay, so what would I say about perpendicular? What about perpendicular?
Perpendicular things always create right angles.
And so what you're saying there is you're giving me the definition of perpendicular, right? So that is, we're just going to call that the definition of, and guess what? We can use symbols here. If you want to write out perpendicular, you can, or you can use the symbol for perpendicular if you want to. Okay? Because they use it, we can use it too, right? So try to make things as easy as you, but if you're going to use the symbol, you got to know what it means, right? If you just write an upside down T, you make sure you know what you're talking about. Now, we got to make one more statement. We know B is 90, we know C is 90, so what can I say about B and C? They are congruent. So I'm going to say angle B is congruent to angle C. And if we go back, what I will tell you is sometimes if you don't want to memorize the names, like what's the name of that theorem, you can just state what it says. All right angles are congruent. And so for me, that sometimes is a little bit easier. So you don't have to memorize like names of a theorem. Okay. One other thing, while we're still in the notebook, and then we're going to do one other proof here in